Good evening, everyone, and welcome to today's webinar, Hydrogen as an Energy Carrier for the Near Future, with Dr. Athanasios Stubos. My name is Trifonas, and I will be your host for today. Today's webinar is being recorded and will later be uploaded in our YouTube channel. During the main lecture, you can drop your questions in the chat box below, directed to me, and after the lecture is complete, a Q&A session will follow, during which Dr. Stubos will answer all the questions provided by the audience. Also, during the Q&A session, whoever wants can open their camera and ask their question in person. Lastly, I would like to ask you to keep the chat professional at all times. Now, let's have a few words about our speaker, Dr. Athanasios Stubos. He possesses a long experience in hydrogen technologies and holds a diploma in chemical engineering from the National Technical University of Athens in Greece, as well as a Master of Science in Fluid Dynamics and a PhD in Applied Sciences from the Vox Karman Institute for Fluid Dynamics at the Université Libre de Bruxelles. I think, I hope I got that right, in Belgium. Dr. Stubos heads the Environmental Research Laboratory of the National Research Center Demokritos and acts as a director of one of his institutes. He also coordinated and participated in several national and international energy-related projects and industrial ventures. He has also co-authored more than 180 publications in peer-reviewed journals and 24 chapters in books and international editions, as well as a large number of contributions to international and national conferences. So without further delay, let's welcome our speaker, Dr. Stubos. The Zoom is yours.
Okay, thank you very much, and good afternoon, everyone. I would like to thank the organizers of this series of lectures, first of all, for the kind invitation. And I would like also to state right from the beginning that, in my view at least, this kind of subject, hydrogen, I don't know how many of you have heard or have read in some more detail about it, but hydrogen at the moment and its use as an energy carrier is an issue which would be better served if we would hold a Q&A session mostly, rather than a presentation from my part as a speaker. So I hope that at the end of this presentation there will be questions, and I encourage you to ask questions, because only through these questions some of the issues concerning hydrogen can be clarified. The second thing I would like to say before proceeding to the presentation is that yes, over the, I belong to the circle of people that for some reason have been working on hydrogen and related technologies for. I've been working on this for about 20 years. Before that, I was working on, and I have papers at SPE conferences and so on. Some of you know that already. I was working on issues related to oil and gas, in fact, and somewhere around 2000, the year 2000, something happened, and life brings things in its own way, so that I turned my interests to hydrogen. Why was that? Because at the time, at least, and still, there is work to be done which is related to porous media, in fact, because some media in which hydrogen could be stored effectively were actually porous materials. And in that sense, the experience we had in the research concerning porous materials and flow through porous materials, transport through porous materials, we were thinking that we could transfer it to the new field that was opening at that time, and which was concerning hydrogen. That's my story. Now, 20 years later, or something like this, it seems that a boom is happening in what we call hydrogen technologies. And you may be reading in various sites, hearing all over the news, and that the word hydrogen, when someone speaks about energy and the energy mix of the future, of the coming years and the coming decades worldwide. Every second word is hydrogen, and the reason for that, perhaps we can talk about this, following the slides. The reason for that is that you have all these targets, key targets as they call it, for the year 2030 and for the year 2050, mostly in the European Union, but also around the world, targets that aim at reducing substantially, not only substantially, at reducing down to zero up to year 2050, the greenhouse gas emissions. The climate change is the issue behind all these targets, as you know very well. I'm not going to talk to you about climate change. I guess you know and you understand well what this actually means. The issue here is that there are very strict targets for the years 2030 and 2050 as far as the emissions of greenhouse gases are concerned. And for this reason, well, you can reduce, you can use different fuels, and you can start reducing, and also through other approaches, you can start reducing the level of emissions of greenhouse gases. But when you are talking about bringing them to zero, absolute zero, not reducing, lowering, or whatever, but zero, then you are talking, you're obliged to start talking about a radically different thing, a radically different fuel or energy carrier, whatever you call it. You need to have something which, when it is burned, when it gives off its energy content, it is not emitting any carbon or any other greenhouse gas. And then your options in that case are becoming very, very, very few actually. And the most, let's say, at the moment at least, the most plausible of those options is hydrogen. Now, why is that? Hydrogen, in fact, is an enabler, an energy carrier which can be thought of as an intermediary, an enabler to do what? To take, and I hope you see the cursor as I move it, to take renewable energy in the form of solar or wind energy or whatever this might be, hydropower or whatever, and use it down here at the other end whenever you want. Be careful, whenever you want, moments later, minutes later, hours later, days later, weeks later, months later, years later, centuries later, whenever you want. That is a very big plus compared, for example, to other forms of storing renewable energy like batteries. Whenever you want, in as many applications as possible, in transportation, in industry, in buildings, in every kind of activity, because as I said before, the target of zeroing the emissions by 2050 is a huge one. And this is what hydrogen can do. You can produce hydrogen here by a very well-known procedure from school times, from school years. We all remember that we were talking about how to break water into hydrogen, into its constituents, hydrogen and oxygen, through electrolysis, okay? You need electricity, electric current, and you get it from the renewable sources, solar or as I said before, or wind or whatever. You electrolyze water, you get hydrogen and oxygen. Oxygen goes to the air, although you can collect it and use it because it's a business case as well. But anyway, it is given off to the atmosphere. And hydrogen, it has to be stored. So these pictures, these images here are quite old, so don't really look at them. It has to be stored somehow, transported around wherever you want, wherever you want to use it actually. And that can be on board the vehicle, for example, which moves around and uses hydrogen as a fuel, okay, to move around, or on board or a ship or a train or even an airplane, ideally, or use it in industry, okay, in any type of industry which would like to produce its energy, the energy needed for it to operate through the use of a fuel like hydrogen, which does not produce any greenhouse gases. Now, what is happening when you use hydrogen, for example, through a device, through the use of a device which is called fuel cell, and we'll talk about it later. in this device, in this fuel cell, for example, you take hydrogen, you take the same amount of hydrogen that was produced before by electrolysis, the same amount of oxygen from the air, so there is a closed cycle of oxygen, the same amount of oxygen that is emitted here is also used here during the application of hydrogen, the same amount of oxygen, so no loss of oxygen or no gain of oxygen at all, net gain. And you produce electricity, energy in the form of electricity. You get here electricity. This electricity somehow comes from the sun or the wind or any renewable source here, and you get it out here. And the only byproduct is simple, plain, nice water. Because the reaction that takes place here within the fuel cell is exactly the opposite of the electrolysis reaction. It means that hydrogen and oxygen are brought together to give off electricity and water. So that's the cycle. It's a net cycle. You see, you don't use any oxygen, and you don't use any water. The same amount of water that you have used here to produce hydrogen, exactly the same amount is produced during the use of hydrogen, and it returns to the earth, okay, to the atmosphere and the earth in general. So there is also no net use of water in that cycle. It's just an intermediary to take the energy from the sun or from any renewable source and bring it to the consumption there wherever you need it. That's the idea. That's why we call it an enabler. That's why we call it an intermediary, an energy carrier, or whatever you may call it using those terms. So a few words about hydrogen. This is a very light gas, as you know. Okay, and actually the universe by far consists of hydrogen. 75% of the mass of the universe, more or less, is hydrogen. However, in this very small corner of the universe where we live, this planet Earth, it is perhaps one of the very, very few, extremely few places in the universe where hydrogen cannot be found free in its elemental form, so that you use it directly. You take it and you use it. It is on the planet, as you know, it can be found as water, you know, in chemical compounds like water or hydrocarbons or others, but not free. And that is an issue because you need to produce hydrogen. As I said before, as I showed you before, we need to produce hydrogen in order to use it afterwards. It has, though, that is an interesting thing, as a fuel, it is the best fuel of all, by far. Why? Because by weight, you know, in 1 kilogram of hydrogen, you have about 3 times the energy content of 1 kilogram of one of the best fuels that we have, gasoline, for example. Okay, hydrogen has 2.8 times larger energy content in terms of mass, okay, in terms of weight, than any than the best other fuel. However, the situation, this advantage becomes a disadvantage when you consider the energy content in terms of volume, because as it is a very light gas, in order to have 1 kilogram of hydrogen in a certain volume under normal conditions, you need 10 cubic meters or something. So in order to use it efficiently, effectively, for example, on a vehicle, you have to compress it to bring it in a small volume, to bring the mass that you require to use in a small volume. And that is one of the main issues, as well, as we will see. So the industry uses hydrogen for a long time now, for many decades, in various applications: chemical, refining, refineries, iron and steel, other types of industry. So hydrogen is a well-known gas and a well-known element that the industry uses for a long time now. Okay, they know how to deal with it, they know how to treat it, they know all the things about its safety aspects and these kind of things. It's not unknown, it's not new in that respect. This is important to stress. You can produce hydrogen today. Industry produces hydrogen mostly, as you see, by using hydrocarbons. The reforming process of, for example, natural gas or other hydrocarbons. This provides hydrogen in by far most of it. Okay, you see 48%, I think, yeah, from natural gas, and 30% from oil, and 18% from coal. So you see, today 96% of the total production of hydrogen comes from hydrocarbons. This produces, as you see here, 70 million metric tons of hydrogen produced in 2019, emits a lot of CO2, because in the process to produce hydrogen from hydrocarbons, you produce CO2. So you cannot continue using these production processes for hydrogen. You have to use this one here, which is 4%, and it's called electrolysis. And the way I showed you just before, use the electricity from the renewable sources and use electrolysis to produce it as a green hydrogen. Otherwise, you don't gain much. You reduce a little bit the emissions, but certainly this is nothing. If you produce hydrogen from hydrocarbons, then you definitely do not have a fuel or an energy carrier which means zero emissions at all. Not at all. You have to go through electrolysis through the use of the renewable electricity in its production. Otherwise, the story of hydrogen ends here. So keep that in mind. That's the electrolysis thing. I don't want to say more about it. I would like to stress again that electrolysis has the potential to be carbon-free. If it is powered by renewable sources, if it takes renewable electricity, as I said before, that's the message to keep here. And remember that you need something around 50, because there's always a coefficient of an efficiency coefficient. You need about 50 kilowatt hours, if that's a number you would like to know, about 50 kilowatt hours energy to produce 1 kilogram of hydrogen through this electrolysis. And this energy, as I said before, will come from the sun or from the wind or from other renewable sources, hydropower or whatever. To store hydrogen, I mentioned before that this is an issue, because you may need in a car, in one of the hydrogen cars that are mass produced today by Toyota, for example, or by Hyundai, the hydrogen that you need on the car, that is stored on the car in order to have an autonomy of about 650 kilometers or 700 kilometers, something like this. So much better than the best battery cars. And it's an electric car, all right? Remember that. In a car, you need to carry with you 5.5 kilograms or 6 kilograms maximum of hydrogen. Just this. With 6 kilograms of mass of hydrogen, you go 700 kilometers, because as I mentioned before, it's a much better fuel than anyone else concerning its energy content per unit mass. However, as I said also before, the volume is very large for that mass, and you have to do something to store it. Now, you can store it as a compressed gas, and you see here how they look like, these tanks with compressed hydrogen up to 700 bar for a car. They are made of carbon fibers to be light and to be safe also. You can store it in liquid form as a liquid hydrogen, but then you need under normal pressure to go down to very low temperatures, minus 253 Celsius. That's very cold, as you understand, and there is an issue on how to get that low. This is feasible, they can do it, but also how to keep it there. You need a very good insulation, as you understand, around the tank. And there is chemical storage, that is, the hydrogen can be stored, for example, in the metal, in compounds that are called metal hydrides. They are usually alloys, metal alloys, and the hydrogen really is absorbed within the lattice of these alloys. And don't be misled. Actually, you can store huge quantities of hydrogen within this metallic material, and then release it if you heat it up a little bit, and then release this hydrogen back. So this is also a form of storage that has been used for various applications. People, as I said, in industry are using hydrogen for a long time, and they are transporting hydrogen for a long time. You see here, through using trucks or ships or pipelines. There is a lot of experience on how to do that in a safe way. And actually, people have started using or manufacturing vehicles of various types where hydrogen is used. Actually, the space shuttle was, as you know, one of the two boosters was liquid hydrogen. Okay, in order to, and there has been a lot of use by NASA in that respect. Now, today you have buses. Definitely, there are a lot of buses that circulate around Europe which are powered by hydrogen. There are cars, and I'll show some the latest ones just in the next transparencies. And there are trains as well. maybe there is a proposition and an idea to have in Greece also a train, a hydrogen train, electric train without the need of electrifying the line, the railway, an electric train powered by hydrogen in Greece as well soon, relatively soon. So in vehicles, to use hydrogen, you need this fuel cell device, these fuel cells, in order to convert hydrogen by using oxygen from the air as well to electricity. Okay, they in these fuel cells, as I mentioned before, and I remind that what happens is the exactly opposite reaction from electrolysis. In electrolysis, you have water and electric current giving hydrogen and oxygen. Here you have, in the fuel cell, you have hydrogen and oxygen giving water and electricity, and electric current, which is the one which is driving the car. It's an electric car. So you have electric cars which are divided into fuel cell electric vehicles, FCEVs, and battery electric vehicles, BEVs. These are the two kinds of electric vehicles. They are not competing each other. They are complementary, clearly. Battery electric cars are today, at least with today's technology, they are suitable for, you know, within cities and for relatively short distances, and when you know that you will need also some time to recharge the battery of the car. While for long distances, for heavy duty vehicles like buses and trucks and everything like this, specialty vehicles and so on, and for trains and for ships later, perhaps you cannot use batteries there to electrify them. You have to use something else, and this could be very well hydrogen. So they're complementary, and don't look at them as two competing technologies for electric vehicles. They are complementary technologies for electric vehicles in order to have electric vehicles in all possible applications. I'll skip that. That's how a fuel cell electric vehicle looks like today. At least its powertrain. You see here, that's the tank of the hydrogen, where compressed hydrogen is stored, and here is the fuel cell. And from then on, the car is exactly the same as a battery electric car. It has the electric motor, and all the rest are exactly the same. It has also a small battery for reasons of smooth operation, but it's a small battery like the batteries that we have in our gasoline cars today. The first one was mass-produced hydrogen car was by Toyota, Mirai. Mirai means in Japanese the future. And what you see here, it's in Greek, I'm sorry, but what you see here, the three main characteristics of this electric car compared to battery car, for example, that you have zero emissions, that is the same with battery car, that you have a total time needed for refilling the car with hydrogen, and that is 3 minutes, 3 to 4 minutes maximum. You can compare that to the time needed for a battery car for recharging, and that the autonomy you can do by filling once the car, the tank. Here it says 500 kilometers. That was the previous model, the previous Mirai. Today's Mirai, the new model, goes up to 650 or 700 kilometers. And this is it today. This is the new Mirai that I talked to you about. This is the Mercedes car. These are the 4 companies, the 4 car manufacturers that have in their range of products hydrogen-powered cars, and that is the Toyota one. This is the Honda FCX. This is Hyundai Nexo, a very nice car. I have driven all of them, not in Greece. And this is Mercedes, which is not mass-produced yet, but it is there, and it's a very nice car as well. I would like to say a few more things about the heavy-duty vehicles, because that's the market through which, in transportation, hydrogen is expected to be soon entering the market in widely speaking. Now, why I'm mentioning this? There are several hydrogen buses around in Europe, and I would like to show you that when the first ones were produced by European companies, there are 2-3 European companies producing them, in let's say 2010, the price was up here. This is the price in euro, okay, for one of such bus. It was around 1.5 million euro. And this is the number of buses that circulate around hydrogen buses. You see that they are right now 900, almost 1,000 of those. You see that with the years, just by the evolution of the technology, the progress in the technology, and not by the number, because the number remains very small to affect the price considerably. The price has dropped down to around 600,000 a couple of years ago. Now it's even lower. And if anyone will order a significant number of such buses today, internationally speaking, then the price will automatically fall by another 30 or even more, even 40%. So what I wanted to say here is that the price is rapidly approaching the price of a normal natural gas bus, for example. E-fuels, yes, the possibility of using hydrogen and CO2 from unavoidable emissions, that is important, to produce what we call e-methane or e-methanol or e-gasoline, synthetic fuels, is also something that is being considered for the future, for the near future, actually, because this type of fuels could also be used on ships and even on airplanes, where things are much more difficult in order to electrify them. Niche markets like forklifts is something that has been around, especially in the United States, for many years now. Everybody uses forklifts that are working with hydrogen. Otherwise, you need twice the fleet, because when you use batteries, you have half of the fleet working and another half being charged. With hydrogen, you don't need to do that because it has a much larger autonomy, and you need almost half of the number that you would buy if you had a battery electric forklift. Risks and barriers, yes, there are several of those. The main one is, in my opinion, at least, related to the infrastructure, to the fact that you need to have around the fuel and defueling infrastructure. This is a completely different thing than what we have today. You need to have hydrogen refueling stations and not gasoline refueling stations. As you understand, this is a very big change to produce hydrogen, to transport it around, to distribute it, and all these kind of things. The vehicles exist, so the automakers will almost immediately respond if the market will request in large numbers such vehicles. And the costs will go down if this will happen, if the market will request a large number of such vehicles. So in my opinion, at least, infrastructure is the main thing. And you see a picture which is a few years old now, and you see here the hydrogen refueling stations that are in operation or let's say planned to actually there are more today. What I wanted to say here is that they are concentrated in Central and Northern Europe, as you see, while in this part of Europe, the eastern part and the southern part, you don't see any of them, and that is an issue that needs to be reversed. The most notable manufacturers of such hydrogen refueling stations include today Shell, Total, and Air Liquide. You see that the two first are simply oil companies, oil and gas companies, well-known ones. And the third one, Air Liquide, is one of the big gas companies in Europe and worldwide. About the infrastructures, which I said is a main issue for me, I just want to mention that a big need is for compression. You need new alternative methods. The classical, standard, conventional mechanical compressors for gases like hydrogen are not the best ones here for many reasons. They are too noisy, for example, and you cannot have a hydrogen refueling station within an urban network or something like this. So there are issues there, and all these are related to the infrastructure. But for that, I would like just to give you one piece of information which comes from a relatively recent 2018 study that was performed in Germany for the German state, for Germany, to compare the hydrogen refueling and electric charging for infrastructure for vehicles. So if you have hydrogen electric cars, or if you have sorry about that, if you have battery electric cars, what would be the costs needed for a country like Germany in order to accommodate a large number of these two types of electric vehicles. And I will show you just the result. This is a study which is publicly available. You can find it on the internet. It's freely available. An interesting one. But the main conclusion is here. It shows that while the cost, here are the cost, the cumulative investment in billion of euros that for Germany, okay, for a country like Germany, that has to be done if you have this number of electric vehicles in the market. The electric vehicles, as I said before, can be either battery electric vehicles or fuel cell electric vehicles. You see that here is a transition, let's say, period, if I call it like this, where between 1 and 5 million of electric cars in Germany, I repeat, think of a country like Germany, not Greece. In Germany, there the infrastructure required for such a number of electric cars in batteries, in case of batteries, is quite cheaper when compared to hydrogen. And the issue here is that you need to go to hydrogen production based on renewables, which means that you have to add the costs of the facilities that electrolysis facilities that need to be built in order to produce the hydrogen from renewable electricity, as I said before, because otherwise there is no reason to do it. So here, this is the reason why the costs are higher, the infrastructure costs are higher. But then you see when things are moving forward and you have more and more electric cars in the market, 20 million, for example, then the two types of infrastructure, because batteries will then require drastic changes in the electricity network as well, in the electricity grid. Okay, otherwise all these millions of electric vehicles cannot be charged efficiently. So then the comparison between the total needed investments in billion of euros between the two cases, batteries or fuel cells, it's about the same. Let's say it's about the same. And these values of 40 to 50 billions of euros for a country like Germany compare to easily to the billions that the German government is planning anyway and has already approved to spend in Germany for example, the electric grid enhancement or the federal transport infrastructure, that means roads and so on, improvements and things like this. So these values are not crazy. They are not far more different than values, than money that the German government is already planning to spend for the transportation infrastructure and so on. I will not stay. Okay, I will just mention this as well, that you see that this is the CO2 emission per kilometer in the case of fuel cell vehicles, because the vehicle itself is zero, but this considers everything, you know, the production of hydrogen and everything. So it goes to 2.7 grams per kilogram, while for the battery electric vehicles, if you take into account the production of batteries, then this goes to 20.9 grams per kilogram. This is quite lower than today's limit, which is today's threshold, which is 95 grams of CO2 per kilometer, sorry, not per kilogram, per kilometer. But it gives you an idea of what to expect when you have this kind of electric cars on the road. As I said, the study is available publicly. And I will finish by, I hope you will have questions, and I think that one of the questions would be, what about safety? Now, as all fuels, we have to be clear about this right from the beginning, as all fuels that we know, from oil to gasoline to natural gas to whatever, all the fuels have come with dangers, okay, for various reasons. They're flammable and everything like this. So hydrogen as well comes with this. Hydrogen is different though. I mean, I wouldn't say it's more dangerous or less dangerous or whatever, but it's different and has to be treated differently. And everyone who will be buying in the future, perhaps a hydrogen-powered car or anything like this, should get accustomed to a different kind of behavior against the fuel compared to what we do now with natural gas or with oil or gasoline. But I'm showing you here these pictures refer to an experiment. This is a gasoline car, and this is a hydrogen car. Deliberately there has been a leakage, okay, of the fuel here in the case of hydrogen, as you see it on the left, and in the case of the gasoline car. You see that hydrogen, since it is, and then it is set on fire, okay, since it is a very light gas, it really forms a jet, okay, of gas which really moves upward very fast in the air because it's much lighter than the air, and that the flame is really restricted within this rather thin jet as it goes up. And actually, since the concentration limit within air of hydrogen first passes through fire and then through flame and then in explosion, this makes it a little bit safer, although the bad thing for hydrogen is that the concentration range within in air, which is explosive, is larger. The range is larger, is broader than in the case, for example, of natural gas. Anyway, the two things are different, and you see that in 1 minute later the gasoline car explodes, while in the hydrogen case, you see that most of the hydrogen has already left the tank, and that the flame has diminished, and after a while it will go away because hydrogen has already left in the air, up in the air. It doesn't mean automatically that one of the two can be characterized as more dangerous than the other. It's different, as I said before. I just wanted to show you this example, and I wanted to mention, sorry, also that we have developed in our group also, we have one of the few computer codes that are used European-wide, and they are approved in Europe for my colleagues here, Alekos Venetsanos and others, are doing the simulations for the cases of accidents, of potential cases of accidents when you have a hydrogen bus or a hydrogen car moving, circulating around. This is the streets of Stockholm where an accident had happened back in 1983 and so on. So we know how to study and how the gas, how hydrogen behaves, and how to study it in terms of safety. These are two, and I finish with that. These are two texts in Greek. I'm sorry, I should have it in English. But the first one shows, this is by Jules Verne, the Mysterious Island, L'Île Mystérieuse in French, the book, the novel which was written back in 1875. Remember this year. And there the writer was saying that water will be the coal of the future, or the oil of the future, if you wish, and you will be taking energy from water through hydrogen and so on. In the same year, in exactly the same year, so 1875, at the United States Congress, the first time that the law about the use of gasoline or oil, if gasoline was not there yet, oil in the first cars and so on, was trying to pass through the Congress. And this is what the congressman, the member of the Congress, in his speech said about this. And actually, it was not, they rejected the law, and oil came later. Why? Because as it is said here in Greek, this congressman said that what shall we be doing with cars, or that will not have any horses, and that they will be moving with gasoline, with oil, and they can achieve speeds of 14 or even 20 miles an hour, and there will be oil stations in the hands of people that do not know anything about how dangerous it can be, and what about the atmospheric air and how it will be polluted, and that at the end, if you see here, the development of this new form of energy, oil, can push away the use of horses, which is going to destroy our agriculture. So yes, the issue of safety and other issues are always important, but I think that the fear before change, before a drastic change, a radical change, is something that is really taking over people, and that is natural. And this we should keep in mind if we will be thinking in the near future of changing drastically our energy system, or in the next decades or something, because of what we face in terms of climate change. So I will stop here. I think I took something like 40 minutes or something like that. And if you have any questions, sorry if I was talking too much. I said myself that I prefer questions Q&A, but finally I found myself talking for 40 minutes. So if you have any questions, I would be glad to answer them.
Okay, thank you, Dr. Stubos. It was a really interesting lecture. Let's go. Our first question comes from Marios Akritidis. He's the president of our chapter. And he basically asks how to store the amount of hydrogen required for a conventional driving range within the vehicular constraints of weight, volume, efficiency, safety, and cost.
Yes, I said that, I think I mentioned that, for example, if you take the example of the Mirai or the Toyota hydrogen car or Nexo, the Hyundai, they are the two best, I think, at the moment. They need to carry around, when the tank is full, 6 kilograms of hydrogen. So in terms of mass, it's nothing, okay? 6 kilograms, if you want gasoline, there will be much more weight for this. But these 6 kilograms of hydrogen, they are now in the present form of these cars, they are compressed in tanks at the pressure of 700 bar. This compression happens on the hydrogen refueling station, not on the car, of course. The car receives the hydrogen already compressed. And with this, they can go with 6 kilograms, they can go 650 kilometers at least. They say the theoretical, let's say, autonomy is 800 and something, but I'm saying 650 just to be on the safe side. And you can refill it, you can fill the tank of the car from 0 to its full content in 3 minutes. As I said, I have driven those cars and I did it myself, and it took, I don't know, 3 minutes and 15 seconds or something like this. So from the point of view of autonomy, of the tank itself and the charging time and all these kind of things, these cars are very much comparable to gasoline cars, okay? Now, you mentioned also safety. I can tell you that the Hyundai Nexo is, try to look at it through the internet, I mean, try to Google it. The Hyundai Nexo has 5 stars in terms of safety. And even if you shoot, or if you, whatever you do on the tank of hydrogen, if you shoot it or anything like this, it's safe. I showed you deliberately these 2 pictures before about the hydrogen car and the gasoline car, where there is a leakage of fuel and this fuel is set on fire. Just to tell you that in terms of safety, although one would have, you know, especially if you're an engineer, you would be really saying and worried about, you know, the fact that you have that you're sitting on a tank which houses a gas in 700 bar. But believe me, I mean, officially and through all the tests that these cars have gone through, because they have to, okay, otherwise they cannot be circulating in the streets. They are equally safe as, at least equally safe as the other cars. I don't know if I answered the question. So the costs, okay, the last thing is the costs. The cost presently of a Mirai, or presently or last year, I mean, in Japan, it was 54,000 euro. But if you take out, but without any, you know, there is no market for that. So it's just so the company itself says that as long as when there will be wide circulation of such cars and there will be orders, okay, massive orders, that the price will automatically drop by more than 30%. So it will go down to 30, I don't know, 30 something thousands of euros. And if you take into account that, let's take Japan, that the state itself there and the regions, for obvious reasons, are supporting the purchase of such cars for obvious reasons related to climate and environment and so on, by something like I think about 10,000 euro, if I'm not mistaken, or something anyway. The price is brought to around 30,000, can be brought to around 30,000, which is comparable to the battery cars. And keep in mind, for those who have not heard that I don't remember who it was recently, one of the major guy in the automotive industry who was warning, one of the leaders of one of the, I don't remember which one, of the major automakers in the world, who was warning that small cars especially will become very expensive as we move on, regardless of the fuel. If you keep on using gasoline cars, there will be more and more taxes in the coming years until to 2025 or 2030 that will really have the aim, or through the CO2 penalty and so on, that it will really have, or through the threshold for CO2 emissions, that will really have the aim to practically ban them. Okay, I can use this bold expression, to practically ban them from being sold. And if you reach that position, then the only alternatives will be electric cars. And if the only alternatives are electric cars, then you have to compare costs between battery cars and hydrogen cars. And then you will start having a competition, and this will lead to dropping the prices definitely. So you have to think about all these things in a different way than we think today. It's not that, okay, now I can buy a car with 15,000 euros, so this I would like to continue doing this. It is not guaranteed that it will go that way.
Okay, thank you. Next question comes from Aris Vlachogeriakos. He's the treasurer of our chapter, and he asks, which was the biggest challenge during the H2 innovations?
Yes, the biggest challenge, technically speaking, in hydrogen innovations are related to, technically speaking, okay, because there is also the organizational part afterwards, but technically speaking, I think that the biggest challenges are the following. I can think of three right now. The first one is the storage. Or the two first ones are related to storage, in the sense that if the technology continues like this, and you will have to store hydrogen in very high pressures, especially for vehicles, then you understand that in order to compress the hydrogen up to these pressures, you spend a considerable amount of energy. So you spend some energy of the hydrogen itself, or some quantity of the hydrogen itself, for the compression. And there is a need for alternative ways of storing hydrogen, of compressing it if we keep high pressures, or of storing it if we try to find solutions, low pressure solutions. For example, using the solid materials that I mentioned before, like the metal hydrides or other types of solid materials. This could be promising. I don't know for vehicles, because the weight there, if you have in your tank, in your fuel tank, if you have also in addition to the gas, you have also a metal, an alloy of metals, which is like a sponge filling the tank, and which absorbs hydrogen, then you understand the weight is increasing. So I don't know about vehicular applications immediately, but generally speaking, storage of hydrogen in large quantities is an issue. Is a technical issue that is under study, and will be further innovations there. And another issue is related to the infrastructure, as I said, which is mostly organizational. It is absolutely necessary to go through, let's say, production of hydrogen. There in the electrolyzers, technical issues in the electrolyzers, in order to drop the costs actually of the produced hydrogen, which is a real target, a real desired target, have to do with the use of precious metals, so like platinum as catalysts there in the electrolysis device. The use of these has to be diminished. It has already been reduced substantially over the last years. There is still some iridium used, and iridium is perhaps the most critical raw material on Earth at the moment. These are similar issues that batteries face, because as you know very well, the batteries as well have the need for materials that in the case of a general widespread use of electric cars many batteries will have to be produced, and issues of recycling and so on, and of finding the materials that are needed, like lithium and others, will not be easy at all, and it may create issues. So these are similar things. Yes, the infrastructure, deploying the necessary infrastructure for production, for transport, for distribution, for hydrogen refueling stations, for anything. This is a huge change and a huge investment that which has to happen worldwide. And these issues are, the humanity has never done it before in such a scale, to change so swiftly and so fast all the related infrastructures to energy, and have a general worldwide consensus on that, and do it on time, and do it in a concerted fashion. This has never happened before, and this is going to be really difficult, and it requires innovation, although this innovation might not be only technical or purely technical. It may include many other things, behavior of people, politics, strategy, investments, and all this kind of issues, which are still open.
Thank you. The next two questions come from Marios Valavanidis. He is a professor at the Department of Civil Engineering at the University of West Attica. And the first question asks, fuel cells or storing cells? Which technology has more road ahead for evolution?
Yes, I think partly I mentioned something about this in my in answering the previous question, but I will, since this is more specific, and thank you, Marios, for this question. Yes, the fuel cells, from the point of view of recovery, cost of recovery of the metals that are in there, and of recycling and all these kind of things, the fuel cells are an easier case rather compared to the battery cells, and they are easier case because the materials themselves of this type that have to be used in a fuel cell are less in quantity, I mean, and they are simpler in the sense that there's just one or two specific ones that you need to reduce, and the recycling is far more easier. The recycling can be done right now. Well, for batteries, recycling is not cannot be considered as a resolved issue, as you probably know, and I'm sure you know. So from this point of view, the fuel cells are a better case than the battery cells.
And the next question is raw materials for batteries versus raw materials for hydrogen store cells. Abundance, cost of recovery, recycle or extraction.
This is the same. This is the question I just answered, I think, by Marios, right? By Marios Valavanidis, or it's another one. No, this is the question I just answered.
It's the second from him.
But this is what I understood, and this is what I answered at least. So let's go to the next one, because I already mentioned the things about this.
Okay. Next question is from Marius Nitu. He says, is hydrogen beneficial simply because we don't have to use batteries when comparing BEV with FCV? Since we don't have enough capacity yet to generate green energy to satisfy the current electricity consumption, why should we redirect some of that green electricity to generate hydrogen?
Yes. The green electricity, which is renewable electricity, I guess that's the meaning of it. Electricity coming from renewable sources at the moment cannot be in countries like Germany, Denmark, and so on. It cannot be. It cannot enter the grid, the electric grid, fully. It cannot be used fully in the electric grid. A considerable quantity of this has to be rejected. Has to be, because it destabilizes the grid. Renewables, as you know, are intermittent. They go up and down. Wind is blowing now. Seconds later, it stops blowing. Then it blows again, and this kind of thing. So, the electric companies cannot. The grid cannot sustain the full amount of green electricity produced from renewables as such. There is, depending on the case, depending on the place, depending on several things. There's a lot of such energy that is being currently curtailed is the word, practically rejected. The first thing to say then is that you have to store this kind of energy, right? It's well known that you need energy storage methods because of this, to store this kind of green energy somehow. Now you can store it in batteries, but batteries, in the case of batteries, you have to reuse it a few hours later, maximum. Batteries have to discharge a few hours later. You cannot keep the batteries charged for days or weeks. An alternative is to use to convert this energy to hydrogen, to use this energy, this rejected renewable energy, to produce hydrogen, and then use hydrogen whenever and wherever you want, in cars or in industry or any energy application you wish, because hydrogen is very that's one of its properties. It can be used anywhere. You know, it can be used as a fuel, as a raw material in industry, as a, you know, it can be used practically anywhere. That is one issue. You can use hydrogen as a storing medium for curtailed green energy. That is one thing. Now, second, further than that, there are many domains, industrial domains, and domains in transportation where electrification cannot be done using batteries. For example, you cannot have a truck today which can go around with batteries. If you want to go with a truck, with a fully loaded truck today, a big truck, and go at least 200 kilometers, the batteries that you would have to carry with you would be probably weighing 1 ton, and this means that you would be simply using the truck in order to transport batteries back and forth and nothing else practically. So buses to go significant distances, even cars to go significant distances, cannot be electrified with batteries. Industry, steel industry, cement industry, a lot of other metal producing industry, aluminium and copper and everything, very, very important, very significant parts of the industry as we know it, cannot simply get rid of fossil fuels and be electrified somehow. The only possibility there is to have a fuel like hydrogen, which will be used like the fossil fuels or through fuel cells, in order to either produce heat or give energy in other forms like electricity to these industries. There is no other way to do it. So for all these sectors, industrial sectors, transportation sectors, and others, you need to have something. And one of the major proposals right now is to have hydrogen. Otherwise, you will not be able to reduce the emissions from these type of sectors, from these type of industries and the transportation sectors. In ships, for example, you cannot have batteries. There are many examples around where you cannot electrify the sector with the use of batteries. There you need something else. And if you're talking about, I repeat that, about zero emissions in year 2050, then you need something. And this something can be very few things right now. And one of these very, very few things is hydrogen. So you need to produce it, you need to use it afterwards as a fuel. And that is why part of the green energy that you would use for electricity has to go to the production of hydrogen, because electricity cannot be used, I repeat, in many sectors to electrify them and to reduce the emissions down to zero. I don't know if I made myself clear, but you cannot do anything with electricity, right? In most sectors, you cannot use electricity. In most industrial sectors and transportation sectors, you cannot use electricity at the moment directly from batteries.
Okay, Mr. Valavanidis would like to speak because he says his first question was different.
Okay, I can.
No, actually, thanks a lot.
Hi, Marios.
Dr. Stubos. Hi, Thanasis. Allow me to. You can talk, I think.
Yeah, of course.
So it was really impressive and very interesting, your presentation. I'm a fan of hydrogen because I understand. I mean, if you follow a couple of presentations on batteries against hydrogen, I mean, hydrogen has a strong case to support. And actually, what we were thinking about future energy transition era, actually this energy transition is now. It's already
Here.
It's already here, yes. So the first question was when you compare, I understand there are two main problems, let's say, technological problems at the moment in exploiting hydrogen. First is where you store it, and second is where you burn it. So you have the fuel cells and the high store cells. I don't know if the expression is correct. The hydrogen storing cells or hydrogen?
Yeah, in hydrogen storage, you don't call them cells. You call them, technologies, because it's different types of.
There are different types. Okay, so which of these different directions has more road ahead? Meaning, which of those two is not that mature and needs further elaboration?
Yeah. Okay, now I understood. Sorry, I didn't get the question when it was first asked.
But you answered the second question.
Yes, I answered the second question.
I have a third question.
Okay,
similar to the first one. So
okay, so to go to this question of yours, allow me please to say once more, because I don't want to be misunderstood by anyone. The batteries and hydrogen are not, in my view and in my opinion, are not competing each other. They are complementary. So there are sectors where batteries can be more efficiently better used, and they should be used. And there are sectors where batteries cannot be efficiently used, and there hydrogen is the choice for the moment, at least. So I don't want to look at them in a competing manner. I would like to look at them as two complementary possibilities, technologies, right? So I want to make that clear, Marios. It was not
absolutely clear. It's absolutely clear. Yes, it's absolutely clear. That's definite. Yeah.
All right. So then going to your question, these are two separate things: storage and use of hydrogen. Okay, whatever we call it in the cells. Okay, storage, as I said, is an issue because it's a very light gas, and you have to find a way to reduce the volume that you need in order to carry it. Okay, to carry a certain mass of it around. So there are three ways, as I mentioned. The storage thing started from space applications, because hydrogen was used a lot in space applications, as you probably know, for many decades now. And in space applications, they prefer liquid hydrogen. Why? Because they don't mind about the time. They use the space shuttle was using all this booster filled with liquid hydrogen within 1 minute or even less, and then it was done. It had already managed to leave the Earth's gravity and so on. So in 1 minute there was no time for hydrogen to evaporate significantly. Okay, and so they used it there as a liquid because that was the best way to increase its density and to pack it efficiently. Okay, it was like a liquid, like all liquids. So
you mean, sorry to understand, liquid at atmospheric pressure?
Liquid at almost atmospheric pressure. That means a temperature minus 250 Celsius. Okay. So they put it into that. They filled this booster just before the shuttle was taken off. Just 1 minute before they filled it. And then it was taken off. In another minute, it was gone. It was used. The hydrogen was used as a fuel. So in 2 minutes, the hydrogen was used already. There was no time to have significant evaporation or anything like this or anything lost. When I drove the first BMW, the car at the airport of Munich, where there was a hydrogen station, it was back in 2000 and something, 2004. I don't remember well. It was in just a 735 BMW, if I remember well, where they had made a modification. They were still using the internal combustion engine, so they didn't have a fuel cell. They were still using the internal combustion engine. They had hydrogen and they were burning it like gasoline in the internal combustion engine. Okay, and the car was going around. The only difference is that the internal combustion engine has an efficiency of, I don't know, 30-35%, maximum 40%, while the fuel cell that you can use to make it electric from hydrogen has an efficiency of more than 60%. So That is the only difference. Otherwise, you can use hydrogen in an internal combustion engine and burn it, and then water comes out. Okay, hydrogen and oxygen gives energy and water. So they were using that, and they were using this. They were storing hydrogen as liquid again. And the problem is that when you were leaving at the airport, the car, because for example, you were traveling to Greece and then you were returning one week later, although you left the car full of hydrogen, when you were returning in 1 week, the car was almost empty because most of the hydrogen had been evaporated, you know, and there was a valve which is opening, okay, a safety valve which is opening because otherwise the pressure will go high, and opening the valve, almost all hydrogen was gone, and you could not move the car. So they left it. This is not probably a way to store hydrogen for long periods, okay? And then you turn to the two other possibilities. Either you compress it as a gas, but you need to go to high pressures, and that is the issue here. Materials for tanks that will be light, not very, very heavy and something like that, but they will withstand very high pressures. On one hand, and the compression of hydrogen itself, which is an issue as well, or try to find a low pressure solution, as I said before, which is now they use metal hydrides, for example, but for static application, for stationary applications, only not for mobile because it's too heavy, and the automakers do not want to have a tank which weighs. I can tell you the truth because Toyota has made. I was there when they made a test with such a tank in their first cars, and it was 140 kilos heavier or something. At the time, the automakers didn't want to accept this extra load. Today, I personally think that they should have, but anyway, that's not my, you know, they don't ask me for that. So the storage issue is independent of the other thing that you said about the cells, and it goes down to these three possibilities. Basically, there are some combinations of those, like cryocompression, which means that you drop the temperature, make it liquid, but you increase the pressure a little bit so that you don't need to go down to very, very low temperatures to minus 250. You can go around temperatures of dry ice, which, as you probably know, is much easier accessible temperature. Okay, much easier to have a temperature like this. Anyway, these are hybrid ways of storing, but storage is an issue, remains an issue, and depends a lot on the application. Okay, as I said before, for cars right now they have 700 bar for the passenger cars and 350 bar for the buses, trucks, and other heavy vehicles, because simply there they have more space. Okay, and the tank can be larger, so they go up to 350 bar. So that's the situation about storage. Now turning on the.
Sorry, but still, when you compare it to the weight of an equivalent capacity battery, it's lower, even those metal hydrides.
It's with the metal hydrides, no, it's not lower. With the other with the compression, it is lower. If you use carbon fibers, it is lower than the battery.
Okay, and the carbon fibers, don't they have an effect of diffusion because hydrogen?
No, they use a special. No, very, very good question. That is the point, actually. They use a special liner, polymer liner on the interior of the tank. It is already established technology, and they cover the interior so that they avoid the effect that you just mentioned, which is important for this case. So it is well established, and actually it has, as I said before, if you see that there is a Toyota car or a Mercedes or a Hyundai going around in Korea or in Germany or in Japan, and it is allowed to do so, meaning that all the tests, safety tests and so on, have gone through. As I said, it's 5 stars, right? It's like the best cars of their types, of their category, equally safe and all these kind of things. Then you really have to, and I'm saying that I don't know if it sounds a bit funny, but you really have to accept that yes, these are tanks that are really safe as any other kind of fuel tank.
Okay.
Now turning to the cells for the production, the cell can take in the hydrogen from all the various storage types that I mentioned before, if it is a liquid hydrogen or if it is compressed gas or if it is in a metal hydride or whatever. The hydrogen that comes out from these forms of storage, it can go as input to the fuel cell equally. So there is no problem there. That's why I said that they are two separate, let's say, things. Now for the fuel cell, there was a boom in the fuel cells some years ago. Then since hydrogen was a boom, and I say that the automakers have bought fuel cell companies in order for them to be able to produce their own fuel cells, because as you understand, if it is a hydrogen car, the core of this engine is not the electric motor. Everybody can make an electric motor, you know that very well. It's the simplest way of the simplest motor and so on. The core of this car is the tank of hydrogen and mainly the fuel cell. So every car maker, they want to have their own fuel cell companies, as Tesla has its own battery, has bought its own battery company, okay, to produce its own batteries. So when this was done, fuel cells were booming actually, and then there were much of improvement both in costs and in the reliability and so on. But then, since hydrogen was not coming, there was still a delay, you know, and everybody was talking about hydrogen, possibility of hydrogen, but there was no hydrogen. Can you see any hydrogen around? Can you see any? That's why you don't see any hydrogen cars yet. Okay, so hydrogen, they had the fuel cells, but hydrogen was not coming. All these companies, all these people that were producing fuel cells, they really hit the wall in the sense that they collapsed. Okay, they didn't have anywhere to sell. So so they started doing what? They started modifying their cells in order to get as input, as fuel, not only hydrogen, but many other things like methanol initially. Okay, you say who has methanol anyway? Very few, but then natural gas. So now you have a lot of small generators, electricity generators actually, that are especially for backup power systems that are capable of doing, or for homes, okay, that are capable of doing what? Of taking natural gas in. They have a small reformer. The device has a small reformer, turns natural gas into hydrogen, okay, inside the device, and this hydrogen is operating the fuel cell. But overall, if you look at it from the outside, what you put in is natural gas, and you get out is electricity. So then they started selling with this a lot, especially in America, and especially to the army and so on. They started selling a lot of these systems. But the authorities, for example, in the European Union, okay, in the European Commission, do not like this, because and actually because that it gives the opportunity of continuing using natural gas, a fossil fuel, which produces CO2 when it is converted to hydrogen, and it promotes at the end of the day the use of natural gas and not of hydrogen. So there was an issue if they would continue fund the development of such fuel cells, and things were, you know, things in the evolution of fuel cells just went through a difficult period, I think. So now, as of the last few years, when the signal was given that hydrogen is back, and then this effort has continued, and now fuel cells, I think you can find fuel cells depending on there are three main technologies for fuel cells, okay, PEM fuel cells, alkaline fuel cells, which is the old mature one, and the newer solid oxide fuel cells. Now, the fuel cells are becoming more and more reliable, and becoming more and more, especially if you are talking about powers in kilowatts, okay? If you're talking about megawatts, then it's now the time, and there is a lot of funding in that direction. It's now the time to start increasing the size of the fuel cells and of the installations to megawatts and so on, and of the electrolyzers as well. But for smaller applications, I think that now fuel cells are quite competitive. The price has to go down a little bit yet, and electrolyzers as well. The price has to go down, it is true, but I think that the price will go down when the deployment of hydrogen in the market will substantially increase. I don't know, Marius, probably I didn't give numbers or anything, but that's how I can answer at the moment, at least.
Yeah, I got the feeling. I understood. Yeah. So actually, if we can produce and store hydrogen efficiently, then a lot of technologies can absorb
Yes,
it.
then you have gone through most of the
The
steps.
barrier.
required.
So the barrier is the how you store hydrogen
Yes,
in mobility applications.
yes.
And the third question, if we have the time.
Marius, can you hear me?
Hello?
Hello, Andreas. This is Andreas Giotis.
Okay.
So we have some more questions.
Okay, sorry.
Sorry to interrupt you.
No, I took advantage of the microphone, so I will.
Okay, thank you so much. Trifona, can you?
Yes, should I read the next question?
Yes, please.
This one comes from Maria Martha Vakirji Tserkezu, and she asks that you showed the three ways of storing hydrogen. Which one is the most used and also economic for them?
Yes, like I said to Marius previously, presently, from the three ways, the one that has found its way mostly, especially through the transportation sector, is the compressed gas way of storing hydrogen, and this is now becoming definitely the cheapest of the three. But in the future, especially in specific applications, at least stationary applications and so on, I think that lower pressure solutions will prevail. Depending on the size of the storage facility, if you are talking about small quantities, relatively small quantities, then definitely you can do it in lower pressures. If it's a stationary application and you have more space available, you don't need to move around and things like this. If you have huge quantities to store, then people are talking about, there are ways of trying to do it in different, for example, even in underground storage, in salt caverns or in facilities that would be underground and so on. So I believe that there will be, in these stationary applications, not I believe, I'm sure it's lower pressure conditions that will prevail in the form of a gas, for the moment, at least in the form of a gas. Now, another way of storing hydrogen, which I didn't mention because that is not pure hydrogen, is and that should be mentioned, is to use actually, instead of hydrogen itself, liquids like ammonia or some liquids called liquid organic hydrogen carriers, LOHCs. These are different types of organic liquids with long chemical formulas. What is the meaning of this? You can, for example, take ammonia, which is nitrogen and hydrogen, okay? And if you produce it in a green way by electrolysis, as they do in Norway, for example, through hydropower, then you can take the ammonia on a ship, and they are doing this right now in some ships for testing purposes. You can carry ammonia, which can be carried around much easier it's a liquid at minus 30 degrees Celsius, more or less, and it's much easier for it to be transported and so on. And since it is a liquid, its density is good, and it is suitable for use on a ship, for example, or things like this. But at the end, you use the hydrogen in it. Through the fuel cell, ammonia is brought down to nitrogen and hydrogen. Nitrogen goes in the air. Hydrogen is the one which is finally used. The same with these liquid organic carriers, hydrogen carriers. They are liquids, but you get hydrogen out of it somehow, and you use the hydrogen. So at the end, it's hydrogen again. But in order to carry it around, people are thinking that it would be more suitable to use other compounds that are liquid, contain hydrogen, and can release it in a way which is compatible to fuel cells. I would like to mention that because I didn't before. Yeah. Any other question?
Yes, and the next one comes from Tudor Katanoiou. I hope I got your name right. And he asks, which is the highest % of hydrogen that could be mixed with gas in the existing gas transportation infrastructure in EU to be transportation are feasible? In order to achieve the 0% emission, is mandatory to build a new infrastructure dedicated to hydrogen?
Okay, for the first, yeah, that's a good question. For the transition time, which can last a lot actually, okay, decades. I believe that natural gas will be there for sure. And the idea, one of the ideas is that, as the question says, that as Tudor says, that you use the existing natural gas grid in all Europe to also to make it greener, to make the use of the natural gas greener by injecting hydrogen into it. Now, as the question says, the first question is how much hydrogen, how much concentration of hydrogen you can have, how much hydrogen can you mix can you blend with the natural gas in the grid without having to do major changes and modifications in the existing natural gas grid and in the existing machinery on the user side, be it industrial user or at home, or whatever. Now, this percentage is still under consideration, but it seems that up to 6 to 8% you can add hydrogen to the existing natural gas grid without having to do any particular modifications at all on both sides, the pipelines and the users. Now, above that, some demo projects are planned and are being carried out as we speak to see what can be done in that way for a if to go up to 20% even hydrogen content into the natural gas. Like this, you understand that the natural gas can be burnt and emit correspondingly less CO2, because 20% of it will be hydrogen, which doesn't emit, when it is burnt, doesn't emit any CO2. But also, people say that if pure hydrogen is needed somewhere in the north of Europe and cannot be produced there, can be transported through the way I said, through the natural gas grid, and at the end point it can be separated again and be used as pure hydrogen. Even that is considered as a possibility. Now, however, quite rightly, as the question says as well, at some point in the future, yes, there will be probably the need to go to almost pure hydrogen, and at the end of the day to pure hydrogen. And there, in that case, there will be also the need to, besides the existing gas grids, to perhaps create another grid, another separate grid, which could be carrying, which will be dedicated to hydrogen, as Tudor said. Now, when and how this may happen in terms of costs, this is still an open issue. I don't think there is any answer anywhere in the world, definite answer on that. But what I know is that industries, also in Greece, for example, that produce pipelines, have already expressed their interest in order to start getting into the business of producing pipelines for hydrogen, for pure hydrogen transportation, hydrogen-ready pipelines for such type of networks of grids. That's all I can say.
Thank you. We don't have any more questions, but I would like to ask you a last question. And how is Greece able to be a hydrogen productive country? I mean, we are really dependent on our energy needs from other countries. Like we mainly import our oil and gas.
Yes, actually, for countries like Greece, I mean, as I said, and as it is clear, you need to produce hydrogen in a green way. That means from renewables, okay, from renewable electricity, which is usually either solar or wind. Greece is a country that has both, okay, in different places perhaps, or in the same place as well. That there is wind and there is also sun, and that may happen also in other countries, especially in the south, as you understand. Now, although wind is also very much abundant in parts of Northern Europe as well. So any country, any place that has enhanced, increased, very high capacity for renewable electricity can become a correspondingly a high producer of hydrogen. When I say high producer, I mean there will be definitely the need, if hydrogen is going to be widely spread and used in Europe, for example, in all Europe, then there will be definitely, at least for certain parts of Europe, needs of importing hydrogen, because hydrogen produced within Europe will probably not be enough. Areas in the south, North Africa, Middle East, and so on, which are so rich in where electricity, renewable electricity can be so cheap, okay, and so easy to produce, can become producers and exporters of hydrogen. Now, this can be a possibility even for Greece, as you understand, because Greece might be at some point in time, due to its very high renewable electricity production capacity potential, can become a producer of hydrogen, and actually can produce more hydrogen than it needs at some point, or it can be economically more favorable for a country like Greece to export hydrogen within Europe, mostly within Europe, I would say. This is a possibility, yes, but there is no, at the moment, all these are in the air. The European Commission has this scheme for several years now, which is called IPCEI. This means Important Projects of Common European Interest, and it has let's say, dedicated this scheme to, for example, batteries already. So important projects of common European interest in batteries, in microelectronics. Now it has issued a scheme like this for hydrogen technologies. And as we speak, most countries in Europe, they prepare their own plans to be submitted to the European Commission. But we are talking about huge plans, in the sense that the minimum investment, total investment that we are talking about is 1 billion euro, okay, for every country, and that's the minimum. And the minimum energy capacity, energy created, green energy created from renewables and used for hydrogen should be of the order of at least 1 gigawatt. So we are talking about huge projects, huge plans from now on, and this is the only way, as the European Commission puts it, this is the only way to push the introduction of hydrogen technologies and related technologies in the market as soon as possible. Now, where this might lead and how this whole thing will evolve and will develop, I cannot foresee right now. I don't want to, although, as I said, I'm working in hydrogen for many years now, but I don't want to say things that might not prove to be true at the end of the day. So all this is in the making. There is a lot of talking and even in politics now, among politicians, as you know, and among strategists and so on, energy strategists about hydrogen. But things have to proceed further in the market in order for someone to be able to say that yes, it is going to be one of the most important parts of the energy mix of the future around 2050 or something like this, when we should go down to zero emissions for CO2 and other greenhouse gases. So that's what I would like to say at the moment. I don't want to say more because things are in the making, and okay, I wish they go that way, but it is not sure yet. But we will need a breakthrough, okay, a very important breakthrough. If things will not go that way, we will need a very important breakthrough, technological breakthrough in batteries or in other, I don't know, some other type of technologies. Otherwise, at the moment, there is no other option, okay, on the table. There is no other option on the table on how to proceed to electrification and to down to zero emissions. It will be, hydrogen will have its position unless, like I said, there will be a breakthrough, a very important breakthrough in technology that we cannot foresee right now.
Thank you for your answer. And I think we're finished for our Q&A session. And I would like to mention that this lecture is under the SP Gaia Sustainability Program. It's a program aimed at more sustainable technologies and alternative means of energy.
Can
So if you'd like
allow
to
me,
find out about that?
allow me to say just one more word that I have been
Of course.
cooperating for some time now, and some of you know that with some of you actually, with several people and like Andreas and so on at the Technical University of Crete. Also, you have in Chania, you have also the newly found Institute of Petroleum Research, which is also located there, and with which we also very much collaborate. This, I think, gives it is an opportunity for people. It may sound a bit strange, but this is the reality that most, or let's say a significant part of the evolution or of the developments in hydrogen technologies takes place from people and from companies that are related to the oil and gas sector. So the Shell has founded Shell Hydrogen. You know that Total is very much involved into the business of hydrogen fueling stations and so on, and all the others. And it may sound for someone who doesn't really know much about it, it may sound a completely different type of business, but it is not at the end of the day. And I personally, as I said before, I was coming, if you see all my previous publications and everything in the past, they were mostly related to porous media and applications in oil and gas. I just forgot to mention it before, so thanks for the invitation, and I hope that you didn't waste your time listening to this.
Thano, just a short question, if I may ask from the organizers.
Of course, go on.
Since you have, it's the second time you mentioned that you're coming from your porous material transport properties origin. Are the scales comparable? Meaning
No.
that...
No, they're different. They're different. But
so
this is not a major problem. Okay, this is not a major problem. People that work in that field or in other fields related, they are well equipped to to change the scales. It's not something very different from some point of view, and from a certain point of view also. It is not, you enter a field at some point in your professional life thinking that what you already know can be widely applied to the new field. It is the case at the beginning, but then you slightly find yourself, also following the trends there and so on. So it's not only porous media, definitely not. It was at the beginning because we were dealing with a specific part of the storage technology that still is investigating porous media, but then you start looking at other things as you understand. You broaden your scope within the new field, the new sector, and that's how things develop. So, but if you look at it from the more narrow perspective of the porous media world, yes, at some point the scales are different, but Marios, you know very well, I mean, in porous media now you are talking about nanoporous media where you have nanopores. You can talk about micropores, you can talk about macropores, and you can talk about scales from a small membrane to the whole oil field, or reservoir, oil reservoir. Yeah, so you know already in this area the scales are there, all of them, from small to large. So,
and the good thing is that you're dealing with artificial materials, so they're more organized, and you don't have to deal with chaos. And,
they're not natural materials or
no, but the basic processes are the same. Meaning, in transport, is it diffusion or is it transport?
They're both.
Both. Okay. Yeah. Okay. Okay. Thanks a lot. It was really interesting and elucidating. for me.
So thank you, Dr. Stubos, for such an insightful lecture, which was also our last for this season, unless we do something in the summer. And we would like to thank you all for being with us throughout all this year. And we would also like to thank Professor Yotis, our faculty advisor. He left, but we owe him very much throughout this year for helping us organize everything. And I guess we will see you in the next season from September. And thank you again, Dr. Stubos.
Thank you. And have a nice summer then, if it is the last of these gatherings.
You too.
Okay.
So good evening to everyone. Good night to everyone. We'll see you.